just letting everyone know. Yeah, so today we're very excited to have Jan here from KTH, and he does a lot of really cool work on optimization and dynamic matrix multiplication, and with some amazing applications to graph algorithms. So Jan, go ahead.
Yeah, so thanks for having me. So I'm going to talk about a bunch of results for linear programs. So let me quickly define what type of linear program we are considering here. So we are trying to find a solution vector X that minimizes the inner product with a cost vector C. And the solution needs to satisfy a bunch of linear constraints that are given by some matrix A. And the entries of X need to be non-negative. And typically, or throughout this talk, if I say M, then that's always going to be the larger of the two dimensions of the matrix that we have. And N is always going to be the smaller one. And if you write some type of graph-based linear program, then typically M is the number of edges and N the number of vertices. So for example, if you have something like minimum cost flow without capacities, then you could write it in this form by saying you try to minimize the cost of your flow. The flow has the linear constraints that everything that goes into a node minus what is going out of a node that needs to satisfy the demand of that node. And additionally, since this is a directed graph, we want that the flow is non-negative so that it actually goes in the correct direction of this directed graph. And yeah, this captures a whole lot of other graph theoretic problems like bipartite matching, shortest path, and so on. But I'm not just going to talk about graph applications, also general linear programs. So let's briefly look at what type of upper and lower bounds exist. So on one hand, we have these linear constraints, right? This is a linear system that has to be solved just to find any vector X that satisfies this. So we have to solve a linear system, which gives this conditional lower bound of, well, we have to read the input matrix, which is of size m by n. Plus, we need to solve a linear system, which currently needs something like n to the 2.373 time. So this is the conditional lower bound for solving linear programs. And in this talk, I'm going to talk about three upper bounds. One is m to the 2.373, which matches this lower bound if we assume that the two dimensions m and n are roughly the same. On the other hand, if one of the dimensions is much larger than the other, then we have this upper bound of mn plus n to the 2.5, where if this is much larger, it's just going to be dominated by the first term, which matches the lower bound. And at the end, I'm going to talk about a graph theoretic special case, which gives a nearly linear time algorithm for bipartite matching if we assume there are at least n to the 1.5 many edges. So these three upper bounds are what I want to talk about here. And all of these upper bounds, they are based on something that's called the central path method. And at high level, you can think of the central path method as some kind of reduction where you reduce the task of solving a linear program to the task of solving a sequence of root m many linear systems. These linear systems have a nice property, and that is this sequence is kind of slowly changing. So any two consecutive linear systems, they're kind of similar, which motivates that you can create some kind of data structure that is able to maintain the solution of this slowly changing linear system. And this is a classic idea, right? You have some iterative algorithm and you try to make it faster by using some kind of data structure. The interesting thing here is that this is actually a cyclic dependency, because when you perform research on these data structures, you might discover some kind of bottleneck. You might discover, oh, I can make this faster if I can use a certain type of approximation. But then you have to go back to the central path method and make sure, is it even possible to approximately solve these linear systems? Is it possible to use this faster data structure? And this creates this cyclic feedback loop where whenever you get a research result on one of these ends, like a better data structure or some new insight for the central path method, it automatically motivates research on the other end because you try to exploit these new insights. And this cyclic dependency is kind of what I'm going to talk about. So specifically, my three results that I want to talk about, they are all just one of these cycles. So the outline of the talk is I'm going to briefly explain the central path method, how that works. And then I'm going to talk about a new data structure, and what modifications we have to perform to the central path method in order to get some fast deterministic linear program solver. Then we use the new insights again to get even faster data structures, which then require further modification to the central path method. That gives us the second result. And at the end, we get again new data structures and some modifications to the central path method, which allow us to get this bipartite matching result. So it's always building on top of each other by modifying always one of these two sides to be even more efficient. Is there a question? No, okay. Right, so the central path method. Before I start with this first section, other questions so far? All right. So the main thing I want to explain in this section is that I claimed we have to solve a bunch of linear systems, which are slowly changing. The exact thing we have to compute over and over again is this somewhat scary looking expression. So let me briefly explain what this expression is. So this matrix A that we have here, that is exactly the constraint matrix of the linear program. So this A is fixed, right? That's just the problem we are currently trying to solve. D here is going to be a diagonal matrix and V is a vector, and only these two values will change over time. So every time we have to solve a linear system and I say consecutive linear systems are similar, what I mean is we have to repeatedly compute this expression here every time this D and this V are going to change a bit. And this expression is kind of going to be the protagonist of this talk because I'm going to repeatedly talk about a new data structure that is able to maintain this, or some new insight for the central path method that is able to relax how D or V are going to change over time. But for now, I just want to explain why exactly this expression is what we have to solve. Okay.
Sorry, a quick question.
Yeah.
Jan. Is A really the same matrix A of the linear program, or this is the same A, or?
So usually it is the same A. There are some, okay, how do I explain this without going into the details? So the central path method kind of tries to refine a solution that you already have, tries to repeatedly improve it. Sometimes in order to construct the initial solution that you are trying to improve, you have to modify the linear program a bit. So then you would add maybe some small identity block to A just so it's easier to find an initial solution that you can improve.
I see.
Think of it as adding some auxiliary edges to the graph with high cost, and so they're not going to be used in the end for the optimal solution. But in general, you can think of that as really just the constraint matrix of the linear program. Yeah.
And really the change here is D basically, no?
It's only the matrix D and this vector V.
V.
Those are the only ones that are going to change over time.
All right. Okay, good, thanks.
Okay. So, right, the central path method. So let's consider again this primal linear program that we want to solve. That's the one I defined earlier. And the geometric interpretation is that all of the points X that satisfy these constraints, they form some kind of polytope. So let's say this polytope is the set of all the possible vectors X that satisfy the constraints. And maybe the optimal solution is the corner up here. That's the point we are trying to find at the end. And for this primal linear program, there also exists a dual linear program where instead of equalities, we now have inequalities. And the nice thing about primal and dual formulations is that for the dual, for these inequalities, we can define a slack vector S, which really just tells us how much space is left for these inequalities. So a slack of 0 would mean that the inequality is actually an equality, like they are tight. And now strong duality tells us if you have a pair for the primal, like an X for the primal and a Y for the dual, then this pair is optimal for both of them if and only if you have that X times S, like every entry of X times the corresponding entry of S is 0. And so for example, this point up here would satisfy this condition. So there also exists some corresponding dual solution such that X times S is equal to 0 for every entry. You could also ask for points that don't exactly have this equal to 0. You could also ask, find a point x and y such that x times s is equal to 1. That's obviously not the optimal solution, but it would be some feasible solution, some point on the interior of this feasible space. And you can indeed ask this for any parameter t, which is going to define a curve that is called the central path, where for t equals 1, you're up here, and when you decrease t, you're moving closer and closer towards this optimal solution. Because if t is equals to 0, right, it's just this optimality condition that we have. All right. Luckily, while it's quite hard to find this optimal solution, it's easy to find a point that has x times s is approximately equal to 1. So it's easy to find some initial point. And now what we're trying to do is we try to improve this solution over and over again. So let's say we have this point and it satisfies that x times s is approximately equal to t, where initially t is this value of 1. Now we're just repeatedly decreasing the value of t. So now this point here is going to be the value that has x times s is equal to t. We decreased t a bit, so it moved closer towards the optimal solution along the central path. And now the point that we actually constructed no longer has this approximation property. So what we have to do is we have to move this point a bit so that again, our solution satisfies that x times s is approximately equal to t. And that's just repeated root m times, because if we decrease the value of t by some 1 over root m factor here, then you need root m iterations to change t by a constant. So by some extra polylog iterations, you get really close to the optimal solution because t gets really small. And this way, we are really just repeatedly moving our point, our solution that we had, to be closer and closer towards the optimal solution until eventually we can say, oh, it's so close, there is just one corner of the polytope that's nearby, we can just round to the nearest corner. That's our optimal solution. Okay. So this is the geometric idea, that we have an initial point and we try to move it along this central path. And the question is, how do you figure out in which direction to move so that you still have these properties? And that's exactly where the linear system comes from. And some of the properties of this linear system are, on one hand, we already had a point x that satisfies these equalities. If we add some delta x to our solution x, we still want it to be an optimal, feasible solution. We still want that the new point satisfies a times x is equal to b. So what we're adding to x must have the property that a times delta x is equal to 0, so that we're not adding anything new and this becomes not equal to b. The next thing is our s, right? If we move this slack vector here a bit, the slack must come from the fact that we moved this dual solution y. So whatever change we have to our slack vector must have come from a change to the y vector, which was multiplied here with a transpose. So that's the second equality here. And if we want to satisfy both of these equalities, then we have to compute exactly this protagonist that I defined earlier, right? Because if delta s is of this form, it's exactly of the form a transpose times some vector here. So we have this equality satisfied. And it's not hard to verify that a times delta x is equal to 0, because if you multiply a with delta x, we get a times v here. And this later term, we get a times d times this a transpose, which is going to cancel exactly with this a times d times a transpose inverse here. So what we're left with is just a times v minus this other a times v. So that's going to be 0. And yeah, I'm not going to define here what exactly would be the right value for this diagonal matrix and this vector v. The important part here is just that it needs to have this form in order to satisfy the constraints. Okay, so the summary here is...
Excuse me, quick question.
What?
So I had a question about, so you may have said it already, but how do you get started? Like how do you
get started? All right. So how do you get? So one idea is that you can kind of add extra constraints to your linear program. When you have this condition, you add some extra columns to A. So it becomes easy to satisfy AX is equal to B by just adding some extra coordinates at the bottom of X. You want that these coordinates are not used at the end, so you make sure that the cost is really high. So if it was a graph LP, right, you're looking for a flow that has certain demands satisfied. You could just add extra edges, so it's easy to construct a flow that satisfies the demand, but you make the cost really high for these edges. So at the end, the optimal solution is not going to use these extra edges. So that's one way to find the initial point.
Right, but you.
Okay, and we also need this property that x times s is equal to 1, right?
Right.
So that can be done with some clever rescaling.
I see.
I can, if you're really interested, I can give you
No. I don't need to see the technical details. I just wanted to understand.
So it's possible by adding some extra constraints or variables and making sure the cost is good, so it's not used at the end, and you perform some rescaling tricks. Yeah.
Okay, and then the other question is that in each iteration you decrease by this factor 1 minus 1 over root n.
Right.
And will we see why that's the
okay?
Right
No, we will not see why that is the right value. For some intuitive idea, it comes from the fact that you need to bound the L2 norm of a certain error that you have. And if you have like epsilon error on each coordinate, the L2 vector is going to be, the L2 norm is going to be root m of something. So you kind of need to divide by what could be the norm of this error vector in worst case, so that the error doesn't get too large.
And will it also be clear from what you're saying that?
So we understood for the rest of the talk is that we have root m iterations, and we have to repeatedly compute this expression here. And later, it's going to be good if you have this geometric idea that we are moving a point along some kind of central path.
Okay.
The details on why it's root m iterations, they are not important.
Yeah, no, that's okay. But the other is that you need to maintain this, the third bullet point, that xi, si is approximately t.
Yeah, so this is what we have to maintain.
And will it be clear from what you described that you are approximately maintaining?
It won't be clear why exactly we are able to maintain this property now.
Oh, okay. All right, that's fine.
So the main thing I just wanted to make clear here was that we have root m iterations. We need this expression here, and only d and v are going to change. And this geometric idea that we move along the central path. These are the only things that need to be remembered for the rest. Okay. All right, so then the first result, right, some m to the 2.373 deterministic LP solver. How can we get this? So let's briefly look at some history of this problem. There exist a bunch of upper bounds for solving linear programs. The complexities are kind of complicated because of the different dimensions that we have. For simplicity, let's assume that the two dimensions are roughly the same. Then the complexity simplified to these terms. And we see that already at the end of the 80s, we kind of got stuck at m to the 2.5 as an upper bound barrier. So even though there were further improvements, m to the 2.5 could not be broken. And that's a very natural barrier because remember what the task was. We have to repeatedly compute this expression here. And what previous algorithms did was they create this data structure that maintains this matrix. Because that's kind of the hardest part here, the fact that we have some kind of inverse here that needs to be repeatedly computed. So past research focused on how to maintain just this matrix efficiently. But the thing is, no matter how efficient you can maintain this, in the end, in every iteration, you have to multiply a vector v with this matrix. And it's not known how to multiply a matrix with a vector faster than in m squared time if it's an m squared matrix. And if we have root m iterations, you need m to the 2.5 total time. no matter how fast you can actually maintain this matrix here. That's kind of where this long-standing barrier came from, until quite recently, Cohen, Lee, and Song have shown that actually this whole central path idea still works if you perform some random sampling on the vector v. So if this vector v becomes sparse because of random sampling, then obviously it's able to compute this product of like a matrix with a vector more efficiently because the vector v is sparse. So that's how they managed to break this barrier. But whenever there's some new idea, some new technique like the stochastic central path, it raises the question, do we really need this technique? How powerful is it? Also with regard to future research, should all future linear program solvers use the stochastic central path method? Or is there also some alternative way? And I've shown that actually you don't need these stochastic ideas. You can get a deterministic result without these new sampling techniques. That's kind of what I want to talk about now, how you can maintain this expression more efficiently without randomly sparsifying the vector v. So, as I said, right, the task is to maintain this expression here. And there already exists an algorithm that over the entire runtime of this linear program solver, it's able to maintain this matrix in m to the 2.373 total time. The old barrier was just, well, how do you multiply the vector efficiently with this matrix? And the new idea now is, all right, instead of just maintaining this matrix, let's maintain this entire product with the vector v. And let's say the vector v changes, we add some small delta v to it, we're just going to change our vector, then you can just expand the product, right? You can just say, oh, it's just the old expression that you already know, plus the new expression, which is just the matrix times delta v. So if the change of the vector from one iteration to the next is sparse, if this delta v is sparse, then you can maintain this later term really efficiently. And that's just something you add to your previous result in order to then maintain this expression here. The issue is that this delta v, like the way v changes, is not actually sparse. So one can show that the exact definition of this vector v is going to be that the ith entry will in some way depend on the ith entry of our solution x and the ith entry of the solution s. And typically, if we move along the central path, it might be that we move in some weird diagonal direction so that every entry of x is going to change. But if every entry of x changes, then every entry of v changes. So then this delta v is a dense vector and we haven't saved anything complexity-wise. So how can you solve this issue? The idea is that we define some, let's say, approximation x tilde of the vector x. And we say every entry of x tilde is going to be some 1 plus minus epsilon approximation of the actual solution x that we have. And Kamaka already back in the 80s has shown that, okay, usually if you define the ith entry of the diagonal matrix with respect to the ith entry of x, it actually also works if you just define it with respect to the approximation. Now I have shown that the same idea even works if you apply this to the vector v. So instead of defining v with respect to this exact x and s, it's fine to just define the ith entry with respect to the ith entry of the approximation that we have. So why does this help? So the idea is, if we move our solution always by some small step, then the most entries of x are not going to change a lot because, right, it's just a small movement that we performed. So if most entries are still roughly the same, then the old approximation that we had is still a good approximation, except for some entries that might have changed a lot. So in this way, you can then argue that delta v is sparse. If you analyze this formally, you can show that the total number of times you have to change any of the entries is bounded by order m. So since v is an m-dimensional vector, you can think of it as, in total, every entry is just going to change on average some polylog number of times. And that's then going to be useful to bound the complexity here of multiplying the matrix with our delta v term.
So total here means throughout the entire algorithm?
Throughout the entire algorithm and all entries, like all the i's together.
All right.
Yeah. All right. So I want to give a brief idea of why you can use this approximation. So notice that this matrix D and the vector V are now defined just with respect to the approximation. So what that means is usually, let's say we have a point that is on the central path. We now just define our step that we perform with respect to some approximate x that we have, which is an element-wise approximation. So we might be somewhere inside this box. If our approximation would be up here in this corner, then if we solve the linear system, if we perform the step, it tries to move us closer towards the central path. So it might try to move us down here. Or if we have this approximation, it might try to move us towards the top left, right? So what could happen is that even though we are already close to the central path, because of our approximation, we might actually move away from the central path. So at first it isn't clear why this works using the approximation, but it turns out that actually it's not an issue if we move away from the central path, because once we are somewhat further away from this central path and we try to move back towards it, what happens is that no matter which approximation we have here, it's always trying to move us towards the top left. So it's always trying to move us towards the central path again. And this in total, what's going to happen is that we will always be able to stay close to the central path, because if we are already close and we have this error, then, well, we might move a bit away, but we only perform small steps, so this isn't too bad. And once we are further away, we are always trying to move back towards the central path anyway. So it's not like this error here can accumulate. So in total, we are still able to follow the central path. So the summary here is that there was this long-standing m to the 2.5 barrier, because you always had to multiply a matrix with a vector. By analyzing the data structure problem, we realized this barrier can be broken if we have some sparse updates to the vector v. And then we had to analyze the central path method to check, okay, can we guarantee the sparsity? And then we realized, yes, that's possible if we just use approximation of the vector x and the vector s. And this way we then get this m to the 2.373 time deterministic LP solver.
So
Right.
what happened? I think I'm missing the approximation. Do you want your approximation ratio to be like 1 over root m so that it doesn't accumulate throughout?
So it's enough if the approximation is element-wise, let's say 1 plus epsilon for some small constant epsilon. Technically, if you do the proof, it needs to be 1 over some polylog value.
Mm-hmm.
But you can think of it as basically some constant factor approximation for every entry.
And still you are going to converge to the actual.
And it still is going to converge. This works because we are just bounding the like the infinity norm of the distance from the point towards the central path.
Okay. All right.
So I have another just kind of big picture question. If you go back to the previous slide. Okay, so when you introduce the approximations, I understand. Am I correct that the purpose was to choose an approximation so that the change in V is sparse?
Right.
Is that correct? So again, that's a detail that we're not seeing is why, how you can take advantage of that flexibility to guarantee that the change in V is sparse. Or did you say something about that?
Okay, right, so here I just explained why it still works, but I didn't explain why it's sparse. So the idea is, let's say you have an approximate value for your x. If you're just going to keep the same, using the same entry over and over again until this entry that you have in your approximation is no longer a good approximation. So you do maintain this x, you do compute this internally, and after every iteration you check, okay, is the difference between x and this approximation for every entry, is the approximation worse than some 1 plus minus epsilon factor? If that's true, only then you change this approximation here. So this way we are going to have as few changes as possible.
So one thing
yeah.
is not clear to me, and again, maybe, we're talking about the change in V, but you're now talking about the change in X. And how is V related to X?
Right. So the ith entry of V is going to depend on the ith entry of X. If you want to know the exact definition.
No, I don't need that. I don't need that. But you're saying that
whenever you change the ith entry of your approximate vector of X, then you're also going to change, only then you are going to change the ith entry of the vector V.
Good. Okay, now I see. Okay. All right. I think that makes sense.
So this was the deterministic LP solver. Then next, we have another cycle where we use the previous insights and modify them a bit to get a fast LP solver if one of the dimensions is much larger. One thing is, what we're going to use here is we are going to approximate some inverse that occurs in the expression. The same type of relaxation we also had in a later paper, but we made it more efficient. Since they're kind of approximating the same thing and the later one is more efficient, I'm just going to talk about the more efficient variant, which is also going to be a reason why the last section is not going to be a full cycle. So just that you're aware, I'm now technically not just talking about one paper, but kind of a merger of these two papers. All right, so this is again about a linear program solver. We had this lower bound, right? And we just talked about how to get some matrix multiplication time upper bound, which is kind of optimal if we assume that this m and this n are the same. But this is quite a strong assumption. Typically, this parameter m can be much larger than n. Think of basically any graph theoretic application. M would be the number of edges. Graph doesn't have to be sparse, right? It could be that m is much larger than n. So let's look at the history again. And this time I'm going to add a column that assumes that one of the dimensions is at least n squared. So one dimension is much larger than the other dimension. It's kind of a tall matrix or a very wide matrix. Okay. In that case, if we look at the complexities that we get, they are all worse than this lower bound. And the lower bound is really just, well, you have to read the n by n matrix. And quite surprisingly, we get a matching upper bound corresponding to the lower bound. And the interesting thing is this is a nearly linear time algorithm, right? Because you have to read the n by n matrix. And that's a somewhat surprising result if you think about that a few decades ago, we didn't even know if solving linear programs can be done in polynomial time. And now it's down to nearly linear. The exact complexity that we have is mn plus n to the 2.5. So there's still a small gap between the lower bound and the upper bound that we have if we don't assume that one of the dimensions is much larger than the other. I want to briefly explain how to get this upper bound.
So just something, n to the 2.5, there is no matrix, fast matrix multiplication in this result?
We do use fast matrix multiplication in here. If you do not use fast matrix multiplication, then the upper bound would be mn plus n cubed.
Okay.
Which would be optimal if you don't use fast matrix multiplication, conditionally optimal if you don't use fast matrix multiplication.
I see.
All right. So how does that algorithm work? I explained previously that we have to repeatedly compute this expression here. I'm going to give a more graphic representation. So every box here is a matrix. And for example, this inverse in the center, the dimensions is much smaller. It's an n by n matrix, but the matrix A is an n by m matrix, and m is the larger dimension. So it's like this wide rectangle, a wide matrix. And we're going to multiply with a vector. Previously, we said we need root m iterations. So we have to repeatedly compute this root m times, but Lee and Sidford a while ago have shown that it can actually be reduced to root n, like the smaller of the two dimensions. Okay, so how can we compute this efficiently? Let's split this into 3 smaller parts, where at first we have to compute V times the matrix. And here we can just use the same trick as before, where we say, oh, V changes in some sparse way, so we can just maintain this product A times V over the entire algorithm in mn time, if we know that the total changes that happen to V is bounded by order m in some polylog factors. So just maintaining this first product, that can be done efficiently. Next, we have to multiply this result with this inverse. Let's assume for simplicity that the inverse is given to us, so we don't have to compute this. Then we have to multiply a vector with an n by n matrix. And well, if we have root n many iterations, that means the total time is going to be n to the 2.5 for this part, because every matrix vector product needs n squared time. And then at the end, we have to multiply with the matrix A again. And that's kind of the hardest part here. So we have a vector that is going to change. It's not going to change in a sparse way, and we have to multiply it with A transpose. How can we compute this product so that it needs in each iteration less than mn time? And for that, we want to look at what exactly is it that we compute here. What we compute here is this delta S, the change that is going to be added to our slack vector of the dual solution. And remember, I claimed that we just need some element-wise approximation of our vector S. Specifically, what that implies is, let's assume we already have some approximation of our vector S. If some entry of S here is going to change by only a small amount, if some ith entry of delta S is really small, then our old approximation is still a good approximation, right? The only thing we really care about are the entries that are sufficiently large of this delta S so that our approximation is no longer a good approximation. So in the end, what happens is the product with A transpose, we don't have to compute this entire product of a vector with this A transpose. We just care about the large entries of this product. And that motivates a new data structure problem. So the task now is we want to find basically A transpose times some vector, all the entries that are larger than some value epsilon times S, because it kind of needs to be multiplicative approximation of S. So how large the value is needs to be relative to the size of S. And the exact data structure problem is, well, you're first given your matrix A, you're allowed to preprocess that at the start of your algorithm. Then over time, this vector S is going to change a bit, this approximation that we have. And in every iteration, we get some vector and we are asked for the large entries. Another way to formalize this is to say, let's say we have a diagonal matrix S tilde, which just has the entries of S on the diagonal. It's multiplied with the inverse here, right? We just basically divide by S on both sides of this inequality. So how can we solve this new data structure problem? What we're going to use here is a sparse retrieval from the streaming and sketching community. They have shown that, let's say you have some tall vector W, you can construct some randomized matrix R, which is really small, like it has the same dimension here as W, so you can multiply it, but it's a really thin matrix. The dimension here is really small. And what this does is it basically projects this W down onto a much smaller space. So we then get this tiny vector Y. And the surprising thing is that even if you only know this tiny vector Y here, you can still reconstruct all of the large entries of this W vector, which is almost exactly what we're trying to solve here, right? We're also trying to find large entries of some vector. So in the end, our data structure is just going to be, let's maintain the matrix M, which is this random matrix R times S inverse times A transpose. And then instead of computing the entire matrix vector product that we had of this tall matrix, we now only need to compute the matrix vector product with this much smaller matrix that we projected down onto a smaller dimension because of this really thin matrix R here. So this way we get this tiny vector Y, and then we can reconstruct the large entries of the vector W, but this vector W is really just S inverse times A times the vector H. That's exactly what we were looking for, the large entries of this vector here. So this is how we can solve this heavy hitter problem efficiently by using these sparse retrieval techniques.
Can you say again why on the left-hand side these are heavy hitters? Why isn't it that every coordinate can satisfy this property?
Right. So the property of the steps that we perform in our what's called in the central path method is that the norm of this vector is going to be bounded by a constant, always.
Ah, I see. Good.
So you just have constant divided by, well, basically another small constant or polylog term.
Good.
Okay. All right, so the summary here is that we need to repeatedly compute this expression, right? And the idea was we split this into 3 smaller parts. The first part can be maintained efficiently via sparse updates to V. This part is efficient because, well, it's a small matrix. It's just n by n. The large dimension m that we have doesn't matter here. And for the last product, we just need to find the large entries. And that's how we get this mn plus n to the 2.5 total time. But right, the assumption here is that this inverse is given to us. Right? I didn't talk about how to maintain this inverse. And that's a strong assumption. The issue is that even without inverting the matrix, right, just computing A D times A transpose, that already needs more than mn time. Even if you use fast matrix multiplication, it needs something like m to the omega minus 1 times n time, which is that's more than mn unless matrix multiplication happens to be like quadratic time. There's a way around this. So a while ago, it was shown that while it's hard to compute this matrix, you can compute an approximation, a spectral approximation H, in well, much more efficiently. So you basically have to read the input matrix NA, so this NM term, plus you only need to multiply matrices of much smaller dimension. So the idea is, instead of using the inverse here of A, D, A transpose, what we want to use is the inverse of this approximation here, because this approximation is much easier to compute than this ADA matrix. The problem is, can we actually use this approximation here? So we have to analyze a bit the central path again to make sure that this is feasible. For this, I want to use the following geometric interpretation. Previously, I said, right, we have a solution, we try to move it along the central path. This here on the right is supposed to be the same picture, but kind of rotated. So think of this as a polytope. It's 2-dimensional, but it's embedded in 3-dimensional space. Here on the left, you're looking at this head-on. And here on the right, we're kind of rotating it by 90 degrees. So you're looking at this from the side. And now here, maybe you see it as a blue line. That's the central path. When we perform one step, we're trying to perform one step inside the polytope because we always try to have a feasible solution. We always want to stay inside the polytope here. And then I said, okay, this movement that we perform, we are moving delta x by this expression here, because what this expression has as a property is that a times delta x is equal to 0. This way, we make sure that these linear constraints that we have are always satisfied. And I previously argued already that, well, this is because if you multiply a with delta x, you have this AV term. Here, ADA is going to cancel with the inverse, so it's really just AV minus AV. That's why it stays feasible. One interpretation of this would be to say, we have our point x, we first move it by the vector v. By moving by v, we are not a feasible solution anymore, so we have to project back down into the polytope. So what we're computing here is really just a projection back into this feasible space that we have. So now the question is, what happens if we replace this inverse with an approximation? And there we get into trouble because now this ADA expression here no longer cancels with the inverse because this is not exactly the inverse that we require. It's just an approximation. So there's going to be some small error. Geometrically, you can think of it as we are moving by v, we're trying to project back down into our feasible space, but because of an approximation error, we might move a bit too far, or maybe we move a bit too little. So we don't end up exactly inside the polytope anymore. And that's a problem because we have to do this over and over again, right? We have several iterations. What could happen is that the error just accumulates. We are moving further and further away from our polytope. So at the end, whatever our point is, it just doesn't have anything to do with the optimal solution that we're actually trying to find because we're just so far away from our polytope.
So what
So this
was
is
the
the issue.
notion of approximation between H inverse and ADA transpose?
This is a spectral approximation. So if you take some vector h and you multiply, oh, h is already used there, some vector y, and you multiply y from both sides, then it's going to be some 1 plus epsilon approximation compared to if you multiply y from both sides with this matrix.
All right, good.
All right. Yeah, so the issue is the error can accumulate. We don't have anything that's close to the optimal solution. How we want to fix that is, well, the idea here was we are trying to project back down by removing this error that we get from the vector v. Let's try to actually remove the entire error that we have. So when we move our point x that we have by v, we are not just trying to project this error from v back down, we're also trying to remove all, like the entire error that we have. Right? We want to have ax equal to b, so that's exactly this infeasibility that we have, kind of the distance that we had from the vector x to the polytope. And this way, what happens is that in every iteration, we try to fix the error that we have, and it no longer accumulates because, yes, it's true, we cannot exactly project back down into the polytope, but at least we are able to reduce the error in every step in such a way that it doesn't accumulate anymore. Yeah. Okay, so this is the idea here, that we kind of modify the step that our central path performs. We modify that a bit by just adding this extra term here at the end. And by using this, we are then able to get this mn plus n to the 2.5 LP solver. The idea was, okay, we have a new data structure problem, this heavy hitter stuff, and but we also need to modify the central path method. We need to show that it still works, even if you use a spectral approximation for this inverse in the center expression. Thing is, I skipped a lot of details here, like the paper is over 100 pages long. The reason is that I said the number of iterations is reduced from root m to root n. That actually needs some value that's called leverage score. I'm not going to define that here, but there is some other property that you need to maintain. So you need to construct a new data structure that actually maintains these values that are required. You also have to actually maintain the approximation of this inverse. So far, I just explained you can use an approximation, but I didn't actually talk about how you can maintain the inverse of your approximation of this matrix. And I claimed we always have to add this expression here to our step, but how do you actually compute A transpose times X efficiently in every iteration? So there's a lot more details that you can find in the paper that I skipped here. But the high level idea really is that you try to find these heavy hitters and you use the fact that you can approximate the inverse. Okay. Any more questions to this part before I go to bipartite matching? Okay. So how can you get fast bipartite matching? First, let's look briefly at the history. So let's look at maximum cardinality bipartite matching. So you just try to find the largest matching in your bipartite graph. Over recent years, there was a lot of improvement for sparse graphs that says well, basically n to the some exponent, and recent work just decreased this exponent over and over again. And that raises the question, okay, can we actually get something nearly linear? Can this exponent be decreased all the way down to 1? And we show that this is indeed possible, but only under the assumption that your graph has at least n to the 1.5 edges. So if your graph is moderately dense, then you can get a nearly linear time algorithm. And the nice thing is it also works for minimum weight perfect bipartite B matching, which captures things like negative weight shortest path, for example. Okay, and I want to briefly explain how to get this result here. So what we did was this bipartite matching problem can be written as a linear program. And if you write it as a linear program, then this matrix A that we have, the constraint matrix, is just the incidence matrix of a graph. So here the rows are going to be indexed by the vertices of the graph. The columns are going to be indexed by the edges of the graph. And in each column, we just have a +1 or -1 that is that specifies, okay, is it a directed edge from which two vertices, basically. Just the incident vertices are going to have a +1 and -1 in each column. All right. And we are now basically following the idea of this tall LP solver. We're just trying to make it more efficient by using the insight that this is not a general matrix, but it's this incidence matrix. So the first thing, again, is we try to maintain this product here by using that V changes in a sparse way. But now we know that additionally, every column here is going to be sparse, right? It has just 2 non-zero entries. So in total, since we know the total number of changes to this vector V are going to be nearly linear, you just have 2 entries per column, right? If an entry changes here, it's just going to be multiplied with 1 column. So for every change, you just need to perform constant time of work. So the total time for maintaining this product is nearly linear time. Next, when we have computed this product, we have to multiply with this inverse here. And the nice thing is, if A is this incidence matrix, then this ADA transpose is exactly a Laplacian. It is a Laplacian of the graph with some edge weights given by this diagonal matrix. And in a previous work with Aaron, we have shown that you can maintain a dynamic spectral sparsifier. Like we can maintain a sparsified version of this Laplacian. And previously we had shown we can use a spectral approximation. So we can just replace this Laplacian here with our spectral sparsifier. Next, since this is a spectral sparsifier and it's a Laplacian, we can just use a Laplacian solver on this sparsifier. So for every time we need to solve a linear system in this inverse, we just need nearly linear time in the number of vertices. And we said we need root n many iterations. So the total time we are going to require for the entire algorithm is going to be n to the 1.5 here. All right. So the only thing that now remains is, okay, after computing all of this, how do we find the large entries of this A transpose times some vector? So we now need to solve this heavy hitter problem for the special case that this is an incidence matrix. All right. So the heavy hitter problem, right, was that we are given this incidence matrix, and after some pre-processing, some vector S is going to change over time, and we try to find the large entries. If we phrase that as a graph theoretic problem, it would be, we are given a graph, which we are allowed to pre-process. We have some weights on the edges, which are going to change over time. And in every iteration, we get some vector H that is defined on the vertices. And now we are trying to find all the edges where the difference between the uth entry of H and the vth entry of H is going to be larger than this epsilon times W term. Right, so this is the graph theoretic interpretation of what happens here. And this can be reduced to an even simpler problem. You can show that this can be reduced to the case where G is actually just an expander graph. And you can assume that you don't need any weights on the edges. You just try to find the edges where the difference of the two endpoints is larger than some other constant. The idea of this reduction is that we have shown you can maintain an expander decomposition. So expander decomposition here means you are given this graph and you split this into many smaller graphs. And the nice property is that each of these smaller graphs is an expander, and the weights of the edges in this graph, they're all almost uniform. Like they only differ by at most a factor of 2, which means that, well, you can basically just replace this W by this uniform weight that you have on your smaller expander graph. So it's just the same value epsilon prime that you use for the same expander. So what we need to solve now is this simplified heavy hitter problem, trying to find the large differences on an expander graph. And that algorithm is surprisingly simple. So this is again the problem we try to solve. The algorithm is as follows. We are given this graph G, we assume that's an expander. What we do is we given this vector H and we shift this vector by the all ones vector. So we add the same number to all of the entries. And we do that in such a way that afterwards the vector H is going to be orthogonal to the degree vector. So here degree vector, I just mean a vector of dimension n when every coordinate, it just says what is the degree of the corresponding vertex in our graph. And now we're trying to find the edges where the difference of H is large. Note that we can shift by the all ones vector because we're just interested in the difference. So if all of the entries of H are going to be increased or decreased by the same amount, it doesn't actually change the difference. So shifting by the all ones vector is not going to change the output. And now, instead of trying to find the edges where instead of trying to find the edges where the difference is large, what we're going to do is we just check for every vertex if the corresponding entry is larger than epsilon over 2, and then return all of the incident edges. The idea being, if a difference here is larger than epsilon, then at least one of these two endpoints must have been larger than epsilon over 2. So this way we are definitely going to find all of the edges with this condition, but we might find more because we return all incident edges here. So let's look at the complexity. Are we going to return far too many of these entries here? So we are going to use the Giga inequality. Specifically, if we look at the complexity of this algorithm, whenever an entry of H is going to be larger than epsilon, then we have to return all incident edges. So we spend degree of that vertex amount of time. So we can bound the complexity by this expression here, right? We spend for every vertex degree amount of time if this fraction here is at least 1. So that bounds the complexity. And Giga inequality tells us that this term that we have can be bounded by just the differences of the H squared for every H, scaled by the expansion, but we know it's an expander for some polylog terms, so we can just hide that in the O tilde notation. We get that our complexity is just bounded by this expression. The nice thing is, this here is really just the worst case bound on how many edges do you have to return. How many edges can there be where the difference is larger than epsilon, right? Whenever the difference here squared is larger than epsilon squared, you get a 1 here. So basically, the amount of edges we return is in worst case, is not worse than the worst case bound on edges we would have to return anyway. That's why this is efficient. Right. So the summary here is that we need to maintain this expression. We can do that efficiently on the left side because A is sparse and V changes in a sparse way. For the inverse, we use a spectral sparsifier and a Laplacian solver. And for this heavy hitter part, we can solve that efficiently by decomposing the graph into a bunch of expanders. And instead of trying to find large edges, we try to find large vertices. And that's how we get this n plus n to the 1.5 total time algorithm. This n to the 1.5 term is a bit bothersome, right? It's not a true nearly linear time algorithm. So a major open problem is if you can reduce this term here. Currently, we don't know that. And as a reminder, this term comes from the fact that we have to solve root n many linear systems here. We need root n Laplacian system solves that all need linear time. Okay. And yeah, the entire summary of this talk is that we repeatedly went through the cycle here, right? We said we first have a data structure that is fast if we can sparsify the update to this expression that we have, this vector v. Then we had to check for the central path method if that can be guaranteed, and we realized that can be guaranteed if we use these approximate primal dual variables. That's how we got the fast deterministic LP solver. Then we used this insight that we can approximate the primal and the dual to create new data structures, this new heavy hitter problem. But to make that really efficient, we needed to be able to approximate the inverse. And by showing both of that, we get this fast LP solver for really tall or really thin LPs. And by then creating data structures that are tailored to graph theoretic LPs, we get this fast bipartite matching algorithm. All right, so that's it from my part. And if you have further questions, I'm available.
All right, thank you, Jan. So let's do a virtual clap. And good. Any questions?
So Jan, in the second part, when you use a heavy hitter sketch,
Yeah.
that matrix will work only if it is independent from the vector that we applied.
Right. So there is kind of a oblivious adversary assumption, right, that the vector doesn't depend. So the idea is, let's go back to the page. Right. So the vector W must be independent of the sketch. The issue is that, well, depending on what the sketch is, we might return different entries. So in the next iteration, we might have leaked information of this random matrix. The idea is that we just perform a filter process at the end. So we find all the I with large entries. We might also find some entries that are a bit smaller than this epsilon condition because of like the randomness. What we do is we just verify what is the actual size of that specific entry. Right? You can compute any entry of S inverse times A transpose times H in n time, like the smaller of the two dimensions. So after given the set I, we just verify and make sure that we only return those entries that are really larger than epsilon. We don't return the entries that are a bit smaller. And this way, the output is defined deterministically, and with high probability, we just return this deterministically defined output.
Thanks.
And yeah, the same approach can also be used for the heavy hitter problem with the for bipartite matching, where we have an incidence matrix. So we can guarantee that we are never going to leak any information about some randomness in the expander decomposition. Though I think the expander decomposition works against oblivious adversaries anyway.
Right.
Good. Any other question? All right, let's thank Jan again. And yeah, thanks for the great talk. It was really good.
Thanks.
And thank you to everyone for joining this talk and our seminar this semester. I guess this is the last talk of this semester, and we'll be back next semester. All right, thank you, everyone.
Yeah, thanks, Jan. Really amazing talk.